Today I will be discussing Hardy Weinberg Equilibrium and directional selection. For the purposes of this video, I'll be focusing on a fictitious frog population of 50 with 9 green frogs, 26 yellow frogs, and 15 blue frogs. Here are the genotype frequencies, which is calculated by dividing the present genotype by total population. Moving on to our allele frequencies, it is a very similar concept, but since we are looking at the total number of alleles and not individuals, it will be out of 100. Using the Hardy Weinberg Equilibrium equation, we can use our observed allele frequencies to compute expected genotype frequencies. Now, using this information, let's conduct a chi-square test to see if this population is actually in equilibrium or not according to Hardy Weinberg. Here I've broken down the equation to reflect each genotype and filled in the following table according to those calculations. According to those calculations, this population is consistent with Hardy Weinberg equilibrium given the chi-square value, and as long as the following conditions are met, allele and genotype frequencies will not change, hence why it is called Hardy Weinberg equilibrium. It stabilizes or reaches equilibrium. Okay, so back to our frog population. So these frogs live in a swamp filled with many predaceous species, and if you know anything about frogs, you know that they have lots and lots of predators. Since the swamp is very green, the green frogs are going to have the highest fitness value, and then the yellow frogs, and so on. Given these fitness values, we can calculate the survivors before selection and the frequency of them after selection, and here are those computed values. Okay. Given the change in frequency after selection, we can conclude that this is a directional selection. We started off with a low number of green frogs and has since surpassed the number of yellow frogs and blue frogs based on its fitness value and ability to blend in. And here are my references. Thank you for watching.